Welcome to this explainer. Today, we're embarking on a layered descent into the absolute heart of modern artificial intelligence. We're going to start from true zero, looking at the basic building blocks of unstructured data and slowly journey deeper and deeper until we hit the absolute bleeding edge of database engineering. I know many of you are here to really learn the mechanics, so we're going to take our time and get into all the fascinating details. If you've ever wondered how systems can instantly search through billions of images, documents, or concepts in literally milliseconds, well, you are definitely in the right place. Let's get started.
Okay, here's our roadmap for today's descent. We'll be hitting 6 key layers. First, what are vector embeddings? Second, measuring distance and similarity. Third, the exact search bottleneck. Fourth, navigating graphs with HNSW. Fifth, clustering data with IVF. And finally, compressing vectors with PQ.
So, Section 1. What are vector embeddings? Let's start at the very surface layer here. How do we actually translate the messy, unstructured real world into something a machine can genuinely understand?
You know, unstructured data, think of a photograph, an audio clip, or even a long paragraph of text. It doesn't exactly fit neatly into traditional rows and columns. So we use machine learning models like neural networks to digest all that data and output what's called a vector embedding. Think of this as a highly specific numerical fingerprint. It's basically a long array of floating point numbers, and it's often hundreds or even thousands of dimensions long. But here's the cool part. These aren't just random numbers. Every single dimension represents a specific learned feature of that data. Together, this sequence fundamentally captures the true semantic meaning of the original object.
And since these embeddings are really just coordinates in a massive multidimensional space, we unlock a seriously powerful concept. Proximity equals meaning. Words with similar semantic meanings, like cat and kitten, are assigned coordinates that place them geometrically close to one another in this space. Something totally unrelated, like an airplane, is placed way far away. This is literally the central paradigm of vector databases. We're bridging the semantic gap. We aren't just searching for exact keyword matches anymore. We're actually searching for concepts that are located near each other in space.
But, this brings up an immediate super practical question. In a geometric space with over 1,000 dimensions, how do we actually mathematically prove that two vectors are close together?
Section 2. Measuring distance and similarity. This brings us right to the second layer of our descent, which is the mathematical foundation of all vector search.
So we essentially have 3 primary tools to compute this distance. First up is Euclidean distance, often called L2. This is just the straight line distance between 2 points. It cares about both where the vector is pointing and exactly how long it is. Next, we have cosine similarity. Now this one measures only the angle between 2 vectors, completely ignoring their length. If 2 vectors point in the exact same direction, they are perfectly similar. That makes it absolutely incredible for comparing text documents of completely different lengths. Finally, there's the dot product. This considers both the angle and the magnitude, which makes it highly effective for things like recommendation engines, where the length of the vector might represent, say, a user's overall activity level.
All right, so we've got our coordinates, and we have our mathematical tape measure. If we want to find the closest match to a search query, we just measure the distance to everything in the database and pick the smallest number, right? Well, what actually happens when our database grows to millions or even billions of high-dimensional vectors?
Section 3. The exact search bottleneck. This is where we hit a massive, massive wall. We arrive at the very crisis of scale that makes traditional database technologies completely obsolete for modern AI.
There's a stark contrast between 2 distinct approaches here. The absolute gold standard for accuracy is exact search, or k-nearest neighbors. It guarantees 100% precision because it exhaustively compares your query against every single vector. But mathematically, its time complexity is O of n. If you have a billion vectors requiring millions of floating point multiplications per query, your server will literally melt. It's just computationally impractical. So to survive at scale, we absolutely must transition to approximate nearest neighbor search, or ANN. ANN intentionally abandons the guarantee of perfect accuracy in exchange for dramatic, sublinear speed. It uses intelligent indexing to just skip irrelevant comparisons entirely.
Here is the crucial takeaway. ANN algorithms are the beating heart of all vector databases.
We are purposely trading a tiny fraction of accuracy, say getting 98% perfect results instead of 100%, in order to get those results back in a fraction of a millisecond instead of an hour. The entire goal is to rapidly reduce the search scope.
So how do we pull off this magic trick? The first major way is by structuring our data kind of like a highway system. But how exactly can a graph help us skip millions of irrelevant vectors?
Section 4. Navigating Graphs with HNSW. Let's drop down into our fourth layer. Hierarchical Navigable Small World, or HNSW, is currently the industry standard algorithm for achieving state-of-the-art search speeds and incredible recall.
Think of HNSW sort of like a probability skip list. It organizes all your vectors into a multi-layered graph. The top layers are extremely sparse. They only contain a few nodes connected by really long-range links. Think of these like intercontinental flights. You start your search at the very top, taking wide-area jumps to quickly get to the general neighborhood of your query. Once you can't get any closer on that layer, you just drop down to the next, slightly denser layer. You keep repeating this process, which is called greedy routing, dropping layer by layer until you hit the bottom layer. That bottom layer contains all the data points densely connected by short-range links for high-precision searching.
Now, HNSW is remarkably effective. We're talking lightning-fast queries with 95 to 99% accuracy. But of course, there's a catch. Because it relies on all these intricate graph connections to navigate, the entire graph structure has to be kept in your system's RAM. And if you have a massive data set of high-dimensional vectors, those memory requirements become absolutely astronomical.
Which naturally leads us to wonder, if we just can't afford the memory for a massive graph, what do we do? Is there a way to intelligently partition the space itself to restrict our search?
Section 5. Clustering Data with IVF. Let's go deeper into our fifth layer. Instead of building a memory-heavy web of connections, the inverted file index uses a clustering-based technique. It functions a lot like the index at the back of a textbook.
Let's look at the actual search pipeline to see how this works. During indexing, IVF uses an algorithm called k-means to partition the entire vector space into separate clusters, which are called Voronoi cells. Every single cluster has a center point known as a centroid. All the vectors are then assigned to their nearest centroid. So, when you actually run a search, it's a two-stage process. First is the coarse search. You compare your query only to the centroids. You just find the closest ones. Second is the fine search. You now jump inside those specific, chosen clusters, and you exhaustively compare your query to the vectors inside them. And the best part? You completely ignore the rest of the database.
Now, the true power of IVF all comes down to a parameter called nprobe. This dictates exactly how many of those clusters you decide to search. If you search just one single cluster, it's incredibly fast. But you might actually miss the true nearest neighbor if it happens to be hiding just across the border in an adjacent cluster. If you increase nprobe and search, say, 10 clusters, your accuracy goes way up, but your speed goes down. It's brilliant because you are in complete control of that nonlinear trade-off between latency and recall.
So IVF definitely solves the compute problem by reducing the search space. But here's the reality. 1,136 dimensional vectors still take up terabytes of physical space. How on earth do we store this without completely exhausting our hardware budget?
Section 6. Compressing Vectors with PQ. We have finally reached the deepest layer of our descent today. To truly scale to massive sizes, we have to apply a bleeding-edge, lossy compression technique known as product quantization, or just PQ. PQ is, honestly, an absolute masterclass in data compression. Instead of trying to compress the whole vector at once, it breaks it apart. First, segmentation. It takes a massive vector, let's say 768 dimensions, and splits it into smaller, equal chunks. Next is codebook training. It runs clustering on each chunk independently to find typical patterns, creating 256 representative centroids for each section. Then comes the real magic, encoding. It literally throws away the original floating point numbers in the chunk and simply replaces them with the 8-bit ID, a single byte, pointing to the nearest centroid. Finally, during a search, we use asymmetric distance computation. We leave the search query completely uncompressed, but we can mathematically compute the distance directly against these compressed bytes using lookup tables. This keeps everything blazing fast and incredibly cache-friendly.
By replacing highly precise vector coordinates with these learned codes, PQ can give us up to 64x compression. Think about what that actually means in the real world. A dataset that would normally require 3 terabytes of RAM, which is wildly expensive and totally impractical for most setups, can be squeezed down to fit easily on standard commodity hardware.
And quite often, PQ is combined directly with IVF, creating an IVF-PQ index that attacks both the computational bottleneck and the memory bottleneck at the exact same time. It's a real game changer.
Wow. So, we've descended from the very basic premise of turning semantic meaning into geometry, down through the complex math of distance, through the rapid routing of HNSW graphs, the clever clustering of IVF, and finally into the extreme compression of product quantization. By strategically trading tiny fractions of accuracy for exponential gains in speed and memory, we've enabled AI to search vast, massive universes of data in the literal blink of an eye. Which really leaves us with this final, profound thought. If we can already compress billions of complex human concepts into mere bytes and navigate them in milliseconds, what are the true limits of artificial memory as these architectures continue to evolve? Thanks so much for joining me on this deep dive. Stay curious and keep exploring.